Good morning. We are the group 7 and we are discussing about special relativity.
Lorentz transformation. Galilean and Lorentz transformations are similar in some conditions. At lesser speeds than the light speed, the Galilean transformation of wave equation is just a rough calculation of Lorentz transformations. Electromagnetic waves propagate with the speed of light, work on the basis of Lorentz transformations. It is fundamentally applicable in the realms of special relativity. In contrast, Galilean transformation cannot produce accurate results when objects or systems travel at speeds near the speeds of light. In the case of two observers, equations of Lorentz transformation are x prime equal to y times x minus velocity or v times t or the time. Y prime is equal to y. Z prime is equal to z. And t time is equal to y times time or t minus velocity times x over c squared, where c is the light speed and y is equal to 1 over square root of 1 minus velocity squared over c squared. So as per these transformations, there is no universal time. Time changes according to the speed of the observers. Due to this weird result, effects of time and length vary at different speeds. Galilean transformations are estimation of Lorentz transformations for speeds far less than the speed of light. Lorentz transformations are applicable for any speed. Galilean transformations are not relevant in the realms of special relativity and quantum mechanics. So as per Galilean transformation, time is constant or universal. It does not depend on the observer. On the other hand, time is relative in Lorentz transformation. So the limitation of Galilean transformation. So there are the following cases that could not be decoded by Galilean transformation. First, Galilean transformations cannot disappear the actual findings of Michelson-Morley experiment. Second, it breaches the rules of the special theory of relativity. Third, in Maxwell's electromagnetic theory, the speed of light in vacuum is constant in all scenarios. But in Galilean transformation, the speed of light is always relative to the motion and reference point. It will be varying in different directions. So the difference between Galilean and Lorentz transformation is that Galilean transformation are approximation of Lorentz transformation for speeds very lower than the speed of light. Lorentz transformations are valid for any speed, whereas Galilean transformation are not. So in conclusion, it should always be remembered that the Galilean equations are applicable and physically valid in a Newtonian framework. They are definitely not applicable to the coordinate systems that are moving relative to each other at speeds that approach the speed of light. Galilean transformations formally express certain ideas of space and time and their absolute nature.
Postulate of special relativity. Have you ever used the Pythagorean theorem and gotten a wrong answer? Probably not, unless you made a mistake in either your algebra or your arithmetic. Each time you perform the same calculation, you know that the answer will be the same. Trigonometry is reliable because of the certainty that one part always flows from another in a logical way. Each part is based on a set postulate, and you can always connect the parts by applying those postulates. Physics is the same way with the exception that all parts must be described nature if we are careful to choose that the correct postulate. Then our theory will be followed and will be verified by experiment. Einstein essentially did the theoretical aspect of this method for relativity with two deceptivity, decep- deceptively simple postulate and a careful consideration of how measurements are made. He produced the theory of special relativity. Einstein's first postulate. The first postulate upon which Einstein based the theory of special relativity relates to the reference frame. All velocity are measured relative to some frame reference. For example, a car motion is measured relative to its starting point, or the road is moving over a projectile motion is measured relative to the surface it was launched from, and a planet orbit is measured relative to the star it is orbiting around. The simplest frame of reference are those that are not accelerated and not rotating. Newton's first law, the law of inertia, holds exactly in such a frame. The law of physics seems to be simplest in inertial frame. For example, when you are in a plane flying at a constant altitude and speed, physics seems to work exactly the same as if you were standing on the surface of the earth. However, in a plane that is taking off, matters are somewhat more complicated. In these cases, the net force on an object F is not equal to the product of mass and acceleration of ma. Instead, F is equal to ma plus a fictitious forces. This situation is not as simple as in an inertial frame. Not only are laws of physics simplest in inertial frame, but they should be same in all inertial frame, since there is no preferred frame and no absolute motion. Einstein incorporated these ideas into the first postulate of special relativity. As with many fundamental statements, there is more to this postulate than meets the eye. The laws of physics include only those that satisfy this postulate. We shall find that the definitions of relativistic momentum and energy must be altered to fit another outcome of this postulate. His famous equation E is equal to mc squared. Einstein's second postulate. The second postulate upon which Einstein based his theory of special relativity deals with the speed of light late in the 19th century. The major tenets of classical physics were well established. Two of the most important, the laws of electricity and magnetism and Newton's law. In particular, the law of electricity and magnetism predict that light travel at c is equal to 3.0 times 10 8 squared ms in a vacuum, that but they do not specify the frame of reference in which light is at this speed. There was a contradiction between this prediction and Newton's law, in which velocity add like simple vector. If the latter were true, then the two observers moving at different speed would see the light traveling at different speed. Imagine what a light wave would look like to a person traveling along with it at speed c. If such a motion were possible, then the wave would be stationary relative to the an observer. It would have electric and magnetic field that varied in strength at various distance from the observer but were constant in time. This is not allowed the Maxwell equation. So either Maxwell equation are wrong or an object with mass cannot travel at speed. Einstein conclude that the latter is true. An object with mass cannot travel at speed. The, this conclusion implies that light in a vacuum must always travel at speed relative to any observer. Maxwell equations are correct, and Newton's addition of velocity is not correct for light. Investigations such as Young double slit experiment in the early 1800s had convincingly demonstrated that light is wave. Many types of waves were known and all traveled in some medium. Scientists therefore assumed that medium carried light even in a vacuum, and light traveled at speed relative to the medium. Starting in the mid of 1880s, the American physicist A. A. Michelson, later aided by E.W. Morley, made a series of direct measurements of the speed of light. The results of their measurement were startling. Michelson-Morley experiment. The Michelson-Morley experiment demonstrated that the speed of light in a vacuum is independent of the motion of the Earth about the Sun. The eventual conclusion derived from this result in the light, unlike mechanical wave such as sound, does not need a medium to carry it. Furthermore, the Michelson-Morley result implied the speed of light is independent of the motion of the source relative to the observer. That is, everyone observer light to move at speed regardless of how they move relative to the source or one another. For a number of years, many scientists tried unsuccessfully to explain this result and still retain the general applicability of Newton's law. It was not un- it was not until 1905 when Einstein published his first paper on special relativity that the currently accepted conclusion was reached, based mostly on his analysis that the laws of electricity and magnetism would not allow another speed for light, and only slightly aware of the Michelson-Morley experiment. Einstein detailed his second postulate of special relativity. The speed of light is constant independent of the relative motion of the source. Deceptively simple and counterintuitivity, this and the first postulate leave all else open for change. Some fundamental concepts do change. Among the changes are the loss of agreement on the elapsed time for an event, the variation of distance with speed, and the realization that matter and energy can be converted into one another. You will read about this concept in the following section. Misconception: large constancy of the speed of light. Speed of light is constant. C is equal to 3.0 0 times 108 ms in a vacuum. If you remember the effect of index of the refraction from law of refraction, the speed of light is lower in matter. Section summary. Relative is a study of how different observers measure the same event. Modern relativity is divided into two parts. Special relativity deals with observers who are uniform motion, whereas general relativity includes accelerated relative motion and gravity. Modern relativity is correct in all circumstances and in the limit of low velocity and weak gravitation gives the same prediction as classical relativity. An inertial frame of reference is a reference frame in which a body at rest remains at rest and a body in motion moves at a constant speed in a straight line unless acted on by an outside force. Modern relativity is based on Einstein, who postulated the first postulate of special relativity is the idea that the laws of physics are the same and can be stated in their simplest form in all inertial frame of reference. The second postulate of special relativity is the idea that the speed of light is a constant independent of relative motion of the source. The Michelson-Morley experiment demonstrated that the speed of light in a vacuum is independent of the motion of the earth.
Time dilation. In physics and relativity, time dilation is the difference in the elapsed time as measured by two clocks. It is either due to a relative velocity between them or to a difference in gravitational potential between their locations. When unspecified time dilation usually refers to the effect due to velocity. Albert Einstein's 1905 theory of special relativity is one of the most important papers ever published in the field of physics. Special relativity is an explanation of how speed affects mass, time, and space. The theory includes a way for the speed of light to define the relationship between energy and matter. Small amounts of mass can be interchangeable with enormous amounts of energy, as defined by the classic equation E equals mc squared. What does E equals mc squared mean? It is one of the most famous and well-known equations in all of human history. E equals mc squared translates to energy is equal to mass times the speed of light squared. In other words, wrote PBS Nova, energy and mass are interchangeable. They are in fact just different forms of same thing, but they're not easily exchanged. Because the speed of light is already an enormous number, and the equation demands that it be multiplied by itself, or squared, to become even larger. A small amount of mass contains a huge amount of energy. For example, PBS Nova explained if you could turn every one of the atoms in a paper clip into pure energy, leaving no mass whatsoever, the paper clip would yield the equivalent energy of 18 kilotons of TNT. That's roughly the size of the bomb that destroyed Hiroshima in 1945. Time dilation. One of the many implications of Einstein's special relativity work is that time moves relative to the observer. An object in motion experiences time dilation, meaning that when an object is moving very fast, it experiences time more slowly than when it is at rest. For example, when astronaut Scott Scully spent nearly a year aboard the International Space Station starting in 2015, he was moving much faster than his twin brother astronaut Mark Kelly, who spent the year on the planet's surface. Due to time dilation, Mark Kelly aged just a little faster than Scott, 5 milliseconds. According to the Earth-bound twin, since Scott wasn't moving near light speed, the actual difference in aging due to time dilation was negligible. In fact, considering how much stress and radiation the airborne twin experienced aboard the ISS, some argue Scott Kelly increased his rate of aging, but at speeds approaching the speed of light. The effects of time dilation could be much more apparent. Imagine a 15-year-old leaves her high school traveling at 99.5% of the speed of light for 5 years, from the teenage astronaut's perspective. When the 15-year-old got back to Earth, she would have aged those 5 years she spent traveling. Her classmates, however, would be 65 years old to 50 years, would have been passed on the much slower moving planet. More examples of time dilation. Clocks in airplanes click at different rates from clocks on the ground. Putting a clock on the mountain, thus elevating it but keeping it stationary relative to the ground-based clock, results in slightly different rates. The Global Positioning System or GPS has to adjust for time dilation. Ground-based services have to communicate with satellites to work. They have to programmed to compensate for the time differences based on their speed and gravitational influences. Certain unstable particles exist for a very brief period of time before decaying, but scientists can observe them as longer because they are moving so fast. The time dilation means that the time the particles experience before decaying is different from the time experienced in the rest laboratory that is doing the observations. In 2014, a research team announced the most precise experimental confirmation of this effect yet devised. As described in a Scientific American article, they used a particle accelerator to confirm that time moves slower for a moving clock than for a stationary one. Time dilation equation. Let's see how we can calculate the time difference. The equation for calculating time dilation is as follows. So T is equals to T0 over 1 minus V squared over C2 parentheses 1 half, where T equals time observed in the other reference frame. T0 equals time is in observer's own frame or of reference or rest time. V is equals the speed of the moving object. C is equals the speed of light in a vacuum. So in our problem, we will let V equals 0.95 C, comma, T0 is equals to 10 years, and we will solve for T, which is the time that the Earth-bound brother measures. So T is equals to 10 over parenthesis 1 minus parenthesis 0.95 C parenthesis close parenthesis 2 over C2 close parenthesis 1 half. So T is equals to 10 over 1 minus 0.952 parenthesis 1 half. So T is equals to 10 over 3.312, 312. So time is equals to 32 years. The time that the Earth-bound brother measures. Now let's have a closer look at the equation and determine just what impact the speed of object has on time dilation. We can see that as the velocity is small compared to the speed of light, the quantity v2 over c2 approaches 0, and the equation simplifies. T0 T is equal to T0 over 1, which is simply T. So at relatively slow speeds, our everyday speeds, time dilation is not a factor and Newton's laws are still applicable. Now let's look at the high speeds. Close to the speed of light, from the equation that as velocity increases, the quantity v2 over c2 approaches 1, but will never quite reach it, causing the quantity 1 minus v2 over c2 parenthesis 1 half t0 becomes smaller and smaller, therefore causing the time measured by that other observer t0 become greater, thus making our time appear slower. Refer back to the example. I know it's so confusing. Read it again, think about it, then study graph as below. As one can see in the graph, time dilation starts t0 show up between 0.4c and 0.5c. Also notice that the closer one gets to the speed of light, the greater impact speed has on time dilation. Notice how steep the curve gets towards the end. So, last question. Is time dilation proven? Physicists have verified a key prediction of Albert Einstein's special, rela- special theory of relativity with unprecedented accuracy. Experiments at a particle accelerator in Germany confirmed that time moves slower for a moving clock than for a stationary one in September 19, 2014.
Good day to you all. So today I'll be reporting about length contraction. So length contraction is the phenomenon that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame. So what pasabot ani is kanang ang length sa object which is moving is kanang shorter, and this can only happen when ang object is moving at a fraction of a light speed, kanang almost siya sa speed sa light. And kani siya ma-measure ni if ang kanang ga-measure sa object kay nasa rest frame or zero iyang velocity. And this is also known as Lorentz contraction or Lorentz Fitzgerald contraction, after Hendrik Lorentz and George Francis Fitzgerald, and is usually only noticeable at a substantial fraction of the speed of light. Length contraction is only in the direction in which the body is traveling. For standard objects, this effect is negligible at everyday speeds and can be ignored for all regular purposes, only becoming significant as the object approaches the speed of light relative to the observer. So, ang kanang makita na to kapunay nga kanang pagkapaspas na dagan, for instance mga motor drag race nga na dili man jud nato na mabantayan ng length contraction ana. So ana jud na mabantayan nimo or manotice nimo if the object is moving or approaching to the speed of light. So history niya, length contraction was postulated by George Fitzgerald and Hendrik Anton Lorentz to explain the negative outcome of the Michelson-Morley experiment and to rescue the hypothesis of the stationary ether. Although both Fitzgerald and Lorentz alluded to the fact that electrostatic fields in motion were deformed, Heaviside ellipsoid, after Oliver Heaviside, who derived this deformation from electromagnetic theory in 1888. It was considered an ad hoc hypothesis because at this time there was no sufficient reason to assume that intermolecular forces behave the same way as electromagnetic ones. In 1897, Joseph Larmor developed a model in which all forces are considered to be of electromagnetic origin, and length contraction appeared to be a direct consequence of this model. Yet it was shown by Henry Poincare that electromagnetic forces alone cannot explain the electron stability. So he had to introduce another ad hoc hypothesis: non-electric binding forces that ensure the electron's stability give a dynamical explanation for length contraction, and thus hide the motion of the stationary ether. Eventually, Albert Einstein was the first to completely remove the ad hoc character from the contraction hypothesis by demonstrating that this contraction did not require motion through a supposed ether, but could be explained using special relativity, which changed the notions of space, time, and simultaneity. Einstein's view was further elaborated by Hermann Minkowski, who demonstrated the geometrical interpretation of all relativistic effects by introducing his concept of four-dimensional spacetime. So the formula for length contraction is articulated as L equals L L sub 0 times times the square root of 1 minus v square over c square, where L is the length of an object with is in relativistic speed. So ang L ani ang pasabot ani kay ang kanang ang mo'y gipangita nga length sa katong object na galihok. And ang L sub 0 is the length of an object at rest. Ang pasabot ani kay ang makita sa kanang sa observer or kanang at rest frame kung unsay ang makita sa object kung unsay ang ma-measure ana. And sa c is the velocity of light which is constant, and v is the velocity of the object. That's all that's all for length contraction. Thank you.
Mass energy equivalence. Mass energy equivalence states that all objects have a mass, or massive objects have a corresponding instant energy even when they are stationary in the rest frame of an object, where by definition is motionless and so has no momentum. The mass and energy are equivalent, and they differ only by a constant. The speed of light, c squared. In Newtonian mechanics, a motionless body has no kinetic energy, and it may or may not have other amount of internal stored energy, like chemical energy or thermal energy. In addition to any potential energy it may have from the excitation and field of force. These energies tend to much smaller than the mass of the object multiplied by c squared, which is one of the order of 1017 joules for a mass of 1 kilogram. Due to this principle, the mass of the atoms that comes out from nuclear reaction is less than the mass of the atoms that goes in, and the difference in mass shows up as the heat and the light with the same equivalent energy as the difference in analyzing this explosion. Einstein formula can be used with the E as the energy released and the removed and m as the change in mass. Conservation of mass and energy. The conservation of mass and energy is a universal principle in physics and holds for any interaction along with the conservation of momentum. This classical conservation of mass in contrast is derived by certain realistic resetting. This concept has been experimentally proven in a number of ways, including the conversion of mass into a kinetic energy, a nuclear reaction, and other interaction between the elementary particles. While the modern physics has discarded the expression of conservation of mass and older terminology, a relativistic mass can also be defined as equivalent to an energy of a moving system, allowing for the conservation of relativistic mass. Mass conservation's breakdown with the energy associated with the mass of a particle is converted into the form of energy, such as kinetic energy, thermal energy, or radiant energy. Similarly, kinetic or radiant energy can be used to create particles that have mass, always conserving the total of energy and momentum. Einstein mass equivalence. Einstein did not write the exact formula E equals mc squared. In his 1905 Annus Mirabilis paper, does the inertia of an object depend upon the energy content? Rather, the paper states that if the body gives out the energy L in the form of radiation, its mass diminished by L over c squared. This formulation relates only a change in mass, a change L in energy, without requiring the absolute relationship. The relation conveys with the mass and energy can be seen as two names for the underlying conserved physical quantity. He stated that the law of conservation of energy and the conservation of mass are one and the same. Einstein elaborated in 1946 essay that the principle of conservation of mass proved the inadequate in the face of the special theory of relativity. It was therefore merged the two with the energy conservation principle. This was about years before. The principle of conservation of mechanical energy had been combined with the principle of the conservation of heat. We might say that the principle of the conservation of energy, having the previous swallowed up the conservation of heat, now proceed to swallow the conservation of mass and hold the fourth alone. Mass and special relativity. An object moves with different speed and different frames of reference depending on the motion of the observer. This implies the kinetic energy. In both Newtonian mechanics and relativity, it's frame dependent so that the amount of realistic energy an observed object is measured to have a depends on the observer. The realistic mass of an object is given by the realistic energy divided by c squared. Because the realistic mass is exactly proportional to the realistic energy, realistic mass and realistic energy are nearly synonymous. The only difference between them is the unit that the rest mass of invariant mass of an object is defined as the mass of the object as in its frame when it's not moving. With the respect to the observer, physicists typically use the term mass, though the experiment have shown an object gravitationally mass dependent on its total energy and not just its rest mass. The rest mass is the same of all inertial frame as is independent of the motion of the observer. It is the smallest possible value of the relativistic mass of the object because of an attraction between components of a system which results in potential energy. The rest mass is almost never inhibited, and in general the mass of object is not the sum of the mass of its part. The rest mass of an object is the total energy of all parts, including the kinetic energy as the observer and from the center of momentum frame and the potential energy. The mass adds up in the constituent are at the rest and do not attract or repel, so that they do not have extra kinetic potential energy. Massly particles are particles with no rest mass, and therefore no kinetic energy. Their energy is due only to momentum.